This video will introduce the third part of the series on the basic knowledge of the spectroelectrochemical method, the second part of Introduction of Optically Transparent Electrode. In the first part, we introduced gold and platinum film optically transparent electrodes. This chapter will continue to introduce the following optically transparent electrodes. 1. Mercury platinum and carbon film optically transparent electrode. 2. Metal grid electrode. 3. Porous glassy carbon electrode and porous metal electrode. 4. Thin film grid electrode. Sometimes, in order to expand the cathodic potential area of the electrode, electrochemical reduction of mercury ions on the surface of platinum film optically transparent electrode can be used to form a thin mercury surface by electroplating, which increases the available cathodic potential range, about 300 to 400 mV negative shift, due to the larger overpotential of hydrogen discharging on the surface of mercury. By limiting the amount of mercury deposited, a certain light transmittance can be retained. The mercury film is generally about 50 angstroms thick, and even thicker it will form mercury droplets. This mercury-plated electrode allows the optical monitoring of metal deposition on the mercury film electrode and electrode reactions involving the loss of mercury from the electrode, in addition to the study of electrode reactions with negative potentials. Next, the carbon film electrodes. Preparation. Carbon film electrodes can be prepared by vacuum-deposited carbon films on a glassy quartz or germanium substrate. If the substrate is heated to 450 degrees before deposition, a better electrodes can be obtained. Electrical properties. This electrode presents a larger resistance compared to metal film electrodes. In addition, its electrochemical properties are similar to those of the usual graphite electrode. Light transmittance properties. The carbon film optically transparent electrode on quartz substrate has good light transmittance in the entire UV visible range. In 1967, Murray et al. Reported on the use of a simple optically transparent metal grid electrode to observe the spectral changes in an electrochemical cell during electrolysis and after, when the reactants were completely consumed. The metal grid electrodes used are very fine metal micromesh prepared by an electrochemical deposition step. As shown in Figure 3.1, the 1000 mesh gold micromesh optically transparent electrode is used in a thin layer electrochemical cell for spectroelectrochemical measurement. The light transmittance of the 1000 mesh gold micromesh is about 45% with 17.6 micrometer mesh, 60% for 500 mesh with 39 micrometer mesh and 22% for 2000 mesh with 6.3 micrometer mesh. The size of the gold micromesh electrode in the picture is 1 per 3 cm. The micromesh is sandwiched between two pieces of glass or quartz glass. Each piece is spaced with a narrow strip of adhesive, at the thick black line, applied around its perimeter and bonded with moderate pressure. Then apply a generous amount of adhesive to the edge of the clip to ensure a tight seal and place it in a dry place to dry for a period of time before use. The bottom opening of the thin layer cell allows contact with sample solution, reference electrode, and counter electrode. Suction is applied at A to refill the sample solution below into the thin layer cell. For this design, the internal solution can be easily refilled. It is characteristic of the spectroelectrochemical flow cell currently used. The electrode B is the conductive connection terminal. The measurement of the spectral changes during the oxidation of 3,3-line dimethylbenzidine was successfully performed using this thin layer cell. The time course of the absorption at 438 nanometer was recorded. The metal grid electrode is a very fine metal micro-mesh prepared by an electrochemical deposition step. The advantage of metal grid electrode is that it is a very good conductive electrode with high light transmittance and an unrestricted spectral range. Figure 3.2 shows the scanning electron microscope image of the gold grid. During the electrodeposition process, the bright face is close to the original grid. Platinum grid are not suitable for electroplating preparation, and coarse woven platinum grids is required. The light transmittance of the grid is due to the micropores in the metal. The metal frame is non-transmissive. The light transmittance remains basically unchanged in the entire ultraviolet visible infrared range. Therefore, With optically transparent grid electrodes, the optical properties of the spectroelectrochemical cell are those of other optical cell elements supporting the electrolyte and solvent, which makes grid electrodes useful over a wide spectral range. The electrochemical properties of the metal grid electrode are basically similar to those of the metal electrode, so the gold grid electrode presents the positive and negative potential range of the bulk gold electrode. According to the diffusion of the electroactive material to the electrode, the uniform geometry of the grid gives its dual characteristics, which manifests as the diffusion to a single wire within a short time after the potential step. As shown in Figure 3.3a, the effective electrode area is the microscopic area of the grid, A micro. After a short period of time, depending on the size of the mesh space, the diffusion layers overlap each other, as shown in Figure 3.3b. Then the electroactive material in the mesh holes undergoes completely depleting electrolysis, as shown in Figure 3.2c. The arrow indicates the diffusion direction of the electroactive material, which is the same as that on the plate electrode in Figure 3.2d. The diffusion is effective for the total two-dimensional area of the grid or several geometric areas. The closer the mesh is to each other, the faster the diffusion layers overlap. Therefore, in the chronoamperometric experiment under the semi-infinite diffusion condition, the apparent electrode area calculated from it gradually changes from the shorter time micro value to the longer time macro value. The transition time from a micro to a macro is also in Table 3.1. Diffusion distribution average time is the time for metal grid electrodes with different pore sizes to reach approximately the diffusion time of a planar electrode, which depends on hole size shown in Table 3.1. If the mesh wire is relatively close to the thickness of the thin layer of the solution as shown in Figure 3.2e, in the thin layer pond conformation, after a short period of time, the mesh electrode can be similar to a planar electrode. The made grid requires a long electrolysis time to achieve planar diffusion, as shown in Figure 3.2f. If it is also used in thin layer spectroelectrochemistry, it will inevitably produce exhaustive electrolysis of the electroactive materials in the cavity. In principle, it is inappropriate to deal with it as semi-infinite diffusion. The mercury grid electrode is also produced by electrodeposition of mercury film on the nickel and gold grid substrate. Figure 3.4 is a thin layer current potential curve describing the negative potential limit of different grid electrodes and hanging mercury drop electrode. Since the mercury film slowly dissolves the gold substrate and produces gold amalgam on the electrode surface, in order to maintain the maximum hydrogen overvoltage, the grid electrode must be replated daily in order to maintain the maximum hydrogen overvoltage. One gold grid electrode can withstand 10 to 30 mercury plating. Grid electrode is mainly used for the comparison of optical and electrical parameters of optically transparent electrodes in thin layer spectroelectrochemistry. Table 3.2 shows the comparison of light transmittance and impedance of different optically transparent electrodes. It can be seen that the grid electrode has a large transmission spectral range and low electrode impedance. Metal grid electrode has the advantage of being very good electrodes in terms of electrical conductivity, while at the same time having high light transmission. Also, it has the ability to bend into different geometries and an unrestricted spectral range. One of its disadvantages is the non-transmissive nature of the metallic wires, which obstructed the observation of adsorption phenomena using perpendicularly incident luminosity. Another disadvantage is the complicated diffusion behavior in spectroelectrochemical experiments performed in a short time. ALS provides customers with two types of mesh electrodes, gold and platinum. The gold mesh is 100 mesh, and the platinum mesh is 80 mesh. Mesh refers to the number of holes on the screen per square inch, and 50 mesh means 50 holes per square inch. The higher the number of mesh, there are more holes, and the lower the light transmission rate. 80 mesh platinum wire mesh working electrode light transmission rate is about 50%, 55%. The presence of contaminants on the mesh will affect the light transmission rate and electrochemical reaction characteristics. The cleaning method of metal wire gauze electrode. 1. Electrochemical cyclic voltammetric scanning cleaning method in sulfuric acid. 2. Ultrasonic cleaning method. 3. If there is no ultrasonic cleaning equipment, you can try to use cotton swab with polishing solution to clean the metal wire gauze electrode. The method is convenient and quick, and can effectively clean the surface of wire gauze electrode in a short time. Reticulated vitreous carbon (RVC). Reticulated vitreous carbon is a glass-like carbon with 97% void volume and porous structure, as shown in Figure 3.6. Reticulated vitreous carbon can have different porosity, and when cut into thin slices, their light transmission is comparable to that of mesh grid electrodes. For 1.2 to 0.5 mm thick, 40 holes, light transmission of 13 to 45%. It is essentially constant throughout the UV visible spectrum, and can achieve complete electrolysis of the active material in a very short time because the majority of the solution is inside the porous electrode. Such electrodes are fragile and require special care during operation. Foam-type metallic materials such as nickel porous metal foams can also be cut into thin slices for use as optically transparent electrodes. The above porous electrodes are prepared for easy light transmission and light range length, which can be adjusted within a certain range by selecting different pore sizes and different thicknesses of materials. Optically transparent electrodes made of porous materials are most suitable for measuring samples with weak light absorption and are also mainly used to form thin layer cells due to their complex diffusion behavior in a short time. Finally, we will introduce a modified thin film light transmitting electrode, thin film grid electrode. In the previous article, we introduced that ITO light transmitting electrode can be used for spectroelectrochemical flow cell measurement. However, in terms of optical properties, ITO light transmitting electrode have good transmittance of 70% to 85% in the visible region, but they have absorption of ultraviolet light and cannot be used for spectrum measurements in the ultraviolet range. Gold and platinum film electrodes with quartz glass as substrate can be used for measurements outside the ultraviolet range, but the transmittance of the electrodes is lower, about 10%. In order to improve the light transmission of the metal film electrode, a grid electrode made of gold, platinum, and carbon materials, suitable for spectroelectrochemical flow cells, was fabricated using lithography technology. This is a picture of the actual product of the thin film grid light transmitting electrode. ALS provides grid electrodes with 3 electrode materials mainly for SEC3F spectroelectrochemical flow cell. Spectroelectrochemical flow cell measurements can be conveniently performed by simply clamping the grid electrode in the flow cell and placing the flow cell, and then set it into the SEC2020 spectrometer system. The quartz glass substrate is used as the optical path reference, with 100% light transmission, and the light transmittance of the ITO electrode and the grid electrode, such as gold and platinum, are compared. It can be seen that light in the ultraviolet range cannot easily pass through the ITO electrode. The light transmittance at a wavelength of 280 nanometer is about 10%. However, the transmittance of visible light with a wavelength of more than 400 nanometer can reach more than 80%. In comparison with the quartz glass substrate as the optical reference, with 100% light transmission, the overall light transmission of the grid electrode is only about 30%, but it can be used in the UV wavelength range. This concludes the third part of the series on the basic knowledge of the spectroelectrochemical method, the second part of Introduction of Optically Transparent Electrode.